everybody see okay? Camera's inevitably right in front of somebody. Would it help if I centered it? Does that look okay? You want me to move it some? Okay. All right. Okay, is this on? It's recording. Okay, so here's the type of question you get. Here's a molecule, SnO2. What is the oxidation state of Sn and what is the oxidation state of O2? The first thing you want to do when you're looking at one of these, I think I'll just take you through it. Go ahead and split out the 10, which is going to be a positive ion, and the 2 oxygens. This should look very similar to something we've done before. Once you split them out, you do this like we did before. Notice I've added up the O2 and O2 to -4, and I've left a blank for what goes to the left over here. And I'll mention here, there's no charge on this. It's not a polyatomic ion, but whatever charge is up there in the top right, you want to bring down to the right side of the equal sign.
Do you have access to these slides?
Yeah, I'll upload these PowerPoints. Okay, so if you just looked at this as it is, what needs to go in that parentheses on the left? For this to equal 0, this needs to be +4. There's only one 10 up here, so the +4 goes on the 10. That should look familiar. We almost literally did exactly that in the ion chapter. But what this means is, did I state it here? Yeah, so the oxidation numbers, and they are essentially charges in this compound, are +4 for 10 and -2 for oxygen. So all of that should look familiar. Don't complicate it. It's very, very, very similar to what we've done before. But let me do another one. This is very similar. You see how this one works. I split the 3 oxygens out to get a -6. I split the 2 TAs out. And since it has to be, and there's no charge here, so I've got a 0 on the right side. -6 plus a +6 equals 0, so I have to split that +6 between the 2 TAs. So for TA it's 3+, and for oxygen it's 2+. You're with me so far, right? Okay, this one, you kind of have to recognize that you've got a polyatomic ion there. I will give you the list of polyatomic ions on the test again. You just have to recognize it. The first step here is to split the potassium off from the BrO4. You know that the potassium is +1. Maybe you do at this point. But that tells you, since it was neutral to begin with, there's no charge up here in this right-hand corner, then you know this has to be -1 if this is +1. If you don't do it that way, you can look on that list of polyatomic ions. The charge is there. The charges and the names and the formulas are all there. But if you get that far, we've already found, I told you the ions are just the oxidation state. This plus here for potassium, that is the +1 is the oxidation state or oxidation number for potassium. But now we could continue to work with BrO4 to figure out the rest of them. Let's see what we got. So oxygen, you can go ahead and assume it's always -2. So there's 4 oxygens there, so they add up to -8. And you remember me saying the charge up there has to go on the right side of the equal sign. So there's a negative up there, so I've got a -1 on the other side of the equal sign. You with me? So now what has to go in this parentheses? Anybody? +7. Yeah, that's right. +7 has to go here, and that will make this equal -1. There's only one bromine there, so the +7 goes on that. So the answer to this is potassium, its oxidation state is +1, bromine is +7, and oxygen is -2. I'll show you what we do with these when we do reactions. So maybe this seems redundant, but here's another one, K2, and that's osmium 04. OS 04 probably isn't on that polyatomic ions list, just because it's kind of an obscure one. But again, all you're going to do is pop off those two potassiums and put the plus and the plus there. And again, potassium is going to have an oxidation state of +1. Now we've got the osmium here, and you just do this and you figure out that it's O6. Notice that I put -2 on the right side of the equal sign, because osmium 04 was 2 negative. Are you with me? We know that osmium 04 was 2 negative because we took 2 positive charges off, namely the potassiums. So we knew this had to be -2. So I put the -2 down here, I added up my charges from oxygen, and if you completed the math, you would figure out that +6 is what has to be here. There's only one osmium, so potassium oxidation state is +1, osmium is +6, and oxygen is -2. Here's just a bunch more examples. Let's see. Let's go over here. Na3PO4. PO4 is on your polyatomic ions list. It says 3 negative for it. I split the sodiums out here. The oxidation state on sodium is +1. And if you follow the rest of my system here, you end up with -8 for the oxygens. You've got the -3 here that needs to come down on the right side of the equal sign. And then that tells you that it has to be a +5 in there. There's only one phosphorus, so it ends up being +5. Again, polyatomic ions are molecules. So that's why most of our attention is focused here, trying to figure out what the charge is going to be on the phosphorus. Another set that you can practice, you know that nitrogen, when it's an ion, is -3. So hydrogen is something to twist here. But really, we have to look at this or this to help you figure out that one a little bit. But I don't think they're really that complicated. But I'll put on the test anyway. H2, this is the first one of these. It's H2. It's one of those I'll put on the board. Its oxidation state will be 0. Look at IO3 here. I did this one the same way I did before. There's a negative sign here, so -1 here. 6 for the oxygens. So if it's going to add the -1, this had to be +5. So iodine is +5. You guys okay with this? Am I going too fast? Okay, redox reactions. What you're trying to figure out with redox reactions is you'll have a reaction. Here's a bunch of reactions that I'm going to go into in a second. And you have to figure out where the electrons will go. This mnemonic oil rig has showed up in textbooks everywhere. Oxidation is loss of electrons, and reduction is gain of electrons. I always remember this. I didn't use oil rig as a mnemonic, but what we're talking about that's being reduced in the process of reduction is the charge. And if electrons are negative, if electrons join an atom, it's going to bring down, that is, reduce its charge. So that's how I always remember it. If you're gaining electrons, you're reducing your charge. So this vocabulary word reduction is referring to the gain of electrons. Unfortunately, oxidation doesn't suggest the loss of anything, but that's a historical anachronism, really. Years and years ago, they thought oxygen is the only thing that would do this, and they subsequently figured out that it isn't just oxygen, but the name stuck. So I always remember that it's oxidation reduction, redox. Reduction means reduction in charge, that is, it's gaining an electron and thereby reducing the charge. And then it has to be the flip side for oxidation, that means loss of electron. So those vocabulary words are worth knowing, but let me get to why this gets confusing for people. So all of these reactions, you could practice these just by looking at this page. The blue page with all the reactions on it, right under redox reactions, in the redox reactions PowerPoint. So you can use this as practice as well as those that I've listed in the back of the chapter. But let me take you through this. All right. If you're just looking at this reaction, and I'm asking you, which of these is being reduced and which of these is being oxidized? If that's the question I'm asking. You look at the equation up here. All right, you see where this says P4, and it's got an S right here? That's one of those where it's a molecule and it's just an elemental molecule, just one type of atom in it. That's when we say its oxidation state is 0. This one is the same way, O2, so the oxidation state of oxygen here is also 0. I hope that's showing up at all there. All right, now we look on the right side here, and we play that game where we split. We've got 10 oxygens. That means we've got a negative 20 here. There's no charge up here, so we need a positive 20 for the phosphorus. And there's 4 of them, so how are you going to split plus 20 into 4 phosphoruses? That means each one of them is going to be plus 5. Did you follow me? I'm trying to avoid writing on the board because of the camera. But here's the idea. If phosphorus is 0 here, and it goes from 0, it reacts, and it goes to a plus 5. Well, let me do oxygen first. Oxygen starts at 0. It goes through the reaction, and when it finishes the reaction, it's at -2. If it has gone from 0 down to -2, it has been reduced. Its charge has been reduced. It gained 2 electrons. You see what I'm saying? So oxygen is undergoing reduction. And that necessarily means that phosphorus is undergoing oxidation. It's losing electrons. Here's the twist, though. So on the left side here, it's all a statement about what happens to phosphorus here. Phosphorus has lost electrons. That's one way you can say it. Phosphorus has lost electrons. Another way to say it is it has had its charge increase from 0 to plus 5. The charge increased because it lost negative charge. Another way to say it is phosphorus has undergone oxidation. You could also say phosphorus has been oxidized. I swear this is what makes redox confusing. It's all this verbiage and wording. It just gets very confusing. So on the next few slides, I stated everything here. Here's the real weird twist. If you're an atom that has the ability to give up electrons, you're an atom who has the ability to force another atom over here to gain electrons. So you can say it is a reducing agent. It can cause reduction in something else while it undergoes oxidation. Because it's giving up electrons, that means something else can gain those electrons. So it's sort of like saying, in the process of oxidation, phosphorus can cause reduction somewhere else. You see what I'm saying? So it's a reducing agent. It's also sometimes called the reducer, and the more fancy word is it's a reductant. All this verbiage is used in redox reactions. Do you follow that? It is very confusing, and I just put the opposite over here on oxygen. It has gained electrons. You can also say it has had its charge decrease from 0 to -2 due to getting those negative charged electrons. You can say it has undergone reduction, its charge is reduced. It has been reduced, but you can also say it is an oxidizing agent because it can facilitate oxidation into something else. Because it's able to accept electrons, it can sort of force something else to give up its electrons. So the oxygen here can be seen as the oxidizing agent. It can be also called the oxidizer, and it's sometimes called the oxidant. You follow I swear what's on this page and those two columns, paragraphs, is the reason this is confusing. The rest is kind of straightforward. There are some other twists, like oxygen can be -1 in some odd cases. I won't give you any of those. And a few other weird twists, but the rest of it works exactly the way I've shown. Let's look at another one. Yeah, I guess I state all that rather explicitly here. Okay, so you see cobalt there. Do you see why cobalt is 0? Its oxidation state is 0, the CO here. It's because it's elemental, there's no other elements there. CO means cobalt, capital C, lowercase o. And chlorine here is 0 as well, because it's elemental as well. And now you look on the other side, you know that chlorine is -1 charge. And you can tell just by inference that the cobalt will be +2. You with me that far? Okay, now we can say that cobalt has gone from 0 to +2, and chlorine has gone from 0 to -1. Therefore, chlorine gained electrons and cobalt lost electrons in the process of this reaction. So chlorine is being reduced. Chlorine is undergoing reduction. Chlorine can also be called the oxidizing agent in this reaction. It can be called the oxidizer, and it can be called the oxidant. And cobalt, it has lost electrons. That means its charge increased from 0 to 3+. It has undergone oxidation. It has been oxidized. You can also say it is the reducing agent. It is the reducer. You can also say it is the reductant. See that? That's the heart of redox reactions. You can practice some more of those. 0. Okay, yeah, look at this one. This one has 3 atoms involved, and one of them doesn't change. So look on the left here, zinc oxide. That's 1 zinc and 1 oxygen. If you pluck them apart, you know that oxygen is -2, so this zinc is necessarily +2. Look at carbon up here. It's carbon with an S in parentheses. It's just pure carbon. That's why I'm going to say carbon has an oxidation state of 0. Now, if you look on the right side, you have zinc by itself. I guess I had a typo in here, so I had to put an S over it. That's why it looks weird. But that's zinc by itself, so its oxidation state here is 0. And if you go over here and go, okay, oxygen is -2, that makes carbon +2. Look at oxygen. Oxygen is -2 on this side, and it's -2 on this side. That means oxygen did not undergo reduction, and it did not undergo oxidation. It really wasn't part of this redox process. But if you look at zinc, it starts at +2 and goes to 0. Here, zinc was reduced from +2 down to 0. So here, zinc is undergoing reduction. Zinc has been reduced. You can also say zinc was the oxidizing agent, the oxidizer, the oxidant. And then the other thing going on here is carbon goes from 0 to +2. So carbon is being oxidized. It's losing electrons. It's undergoing oxidation. You can also call it the reducer or the reductant. That's redox reactions. I guess I'll leave some of these, but all of these in these pages here are these that I have on this blue slide. So you don't have to go and look at the answers right off. You can practice them. There's a weird one. All right. And we also have, still need to upload that. Where did I put up there? 75, 76. So the hallmark of redox reactions is We sometimes call these electron transfer reactions. Not all reactions do this, but some do. And this odd little bookkeeping game we play tells us where the electrons are going during the reaction. We'll build more on this in 1212. If you're taking 1212. All right. Looking at number 75 here. So we see silver here. It doesn't have a charge on it. If you saw this in a reaction, it would probably have an S in parentheses. What's the oxidation state of silver there? It's 0. It doesn't have a charge. But here it is as an ion. What's its oxidation state here? +1. If we took this calcium fluoride and split it out into its ions, what would the charge on fluorine be? They'd be -1. There's 2 of them, so there's a total of 2 negative charges there. But the oxidation state on fluorine there is just -1. It's the charge that it would have if it was an ion. And what is the charge on calcium? 2+, that's the oxidation state of calcium in this molecule. H2S. So that's just like the water molecule I drew over here. S is going to be -2. It's below oxygen in the periodic table. So it'll be -2, and that makes each of the hydrogens +1. In this list, I think it says hydrogen. Hydrogen is +1 when you're assigning oxidation state. Oxygen is -2. I didn't mention this. Where this says group 7A, looking at the PowerPoint for oxidation states from the book, group 7A, I wrote column 17 because the periodic table I gave you all uses this type of numbering system. It says 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's another sort of numbering system where they use these types of code. So I stuck in there column 17. So column 17 is where fluorine, chlorine, and bromine is. Column 16 is where oxygen and sulfur is. And 15 is where nitrogen and phosphorus is. But these are the charges you would expect these to have anyway. Hydrogen might be a tricky one, but it's always -1. Okay, where was I? CO3, if you assume oxygen is -2 and there's 3 of them, that means you have a total of -6 for the oxygen. On the right side of the equal sign will be a -2. So if you've got 2, 4, 6, -6, and then on the other side of the equal sign you've got a -2, what is the positive that you have to add to make -6 equal -2? I'm trying to avoid going to the board. Did you say it? Maybe I can do this in Word real quick so I don't have to change the video. CO3 negative. Make that bigger. So that's what we're working on, and it's this that I'm talking about. All right, there's 3 oxygens. There's 3 oxygens. If they're -2, they add up to -6, right? That 2 negative over there means I'm going to go -2. So what needs to go in this parentheses? 4. That's what I was getting at. So here, oxygen is -2 oxidation state. Carbon is +4 for this one, for E. You guys with me? I'm telling you, it's all that weird wording that messes you up on these. Let's do CR207. Did I do that one? No, CR207. If you've got 7 oxygens, you've got negative 14. The 2 negative up here means you got 2 negative here. There's 2 chromiums there. Well, what needs to go in this parentheses to make the math work out? How do you make the negative 14 equal negative 2? Plus 12. That means you've got to split that plus 12 among 2 chromiums. This should seem familiar from the ion chapter. So chromium is plus 6 here. You see that? I guess there's 2 confusing things about this. One is it looks so similar to ions, you wonder why the heck we're doing this. And the other one is all that weird wording about reductant, oxidant. All right. All right, look at 79C. All right. I think I got to do that one on the board. I just picked that one because it looks like the most complicated one. So let me get us focused on it here.